In this last video, we will learn how to compute the derivative of a function and also some applications that it can have. Let's start by computing a derivative. So suppose we have the function f of x equals x squared minus 4x. Let's try to calculate f prime of x, or also called the derivative of f. So first remember that the derivative of f, it's equal to the limit when h goes to 0 of f of x plus h minus f of x, all that divided by h. So in this case, f is equal to x squared minus 4x, so let's try to put that together. So we want to start with the limit when h goes to 0 of what? We will have x plus h squared minus 4 times x plus h. So that corresponds to the part with f evaluated at x plus h. All of that will be we will subtract from that the original function. So it's x squared minus 4x. And again, everything divided by h. So here we'll have to do some algebra to work with this expression. So first of all, we can expand this squared, and we will get x squared plus 2 times x times h plus h squared minus 4x plus minus 4h minus x squared plus 4x, and all that divided by h. I know this looks a bit long, but some things will cancel. So for example, we can cancel this x squared with this minus x squared, and even more, we can cancel this minus 4x with this plus 4x. So this is equal to the limit when h goes to 0 of what? We will have 2x times h plus h squared minus 4h, all that divided by h. And now to solve this limit, we can factor out h and simplify it with the h in the denominator, because remember, when we consider h approaching 0, we don't actually take h equal to 0. So let's write that down. This will be equal to the limit of what? We will factor out h because every term in the numerator has an h, and that divided by h. So again, we can cancel this. Finally then, this will be the limit when h goes to 0 of 2x plus h minus 4. 2x has nothing to do with h, so that will remain the same. H here will go to 0, so that will disappear. And finally, minus 4 is a constant, so it also will remain the same. So this is saying that the derivative of f, it's equal to 2x minus 4. So the derivative is 2x minus 4. Let's put this into some color. Let's finish this video by looking at an example where the derivative appears in a real-life problem. So let's suppose that the revenue of a company is given by this equation here. So r of x is equal to 200x minus 3x squared, where x is the number of units sold each day. So remember, the marginal revenue is the rate of change of the revenue function. So when they ask us to find the marginal revenue as a function of x, they are asking you to find the derivative of the revenue function. So let's try to do that. So the marginal revenue of x, sometimes denoted as MR, it's equal to the derivative of the function r, which is, again, equal to the limit when h goes to 0 of r of x plus h minus r of x, all of that divided by h. So this will be equal to the limit when h goes to 0 of 200 x plus h minus 3 times x plus h squared minus 200x parentheses all that minus 3x squared, and all this divided by h. So now we can repeat what we did before. I will skip some steps here, and after simplifying the previous expression, you will get that this is equal to 200h minus 6 times x times h minus 3h squared, all that divided by h. Again, we have h in every term on the numerator, so we can simplify h with this by factoring out h. And in the end, we will have that the marginal revenue is equal to the limit when h goes to 0 of 200 minus 6h minus 3h. So again, the marginal revenue will be equal to the limit of 200 minus 6x minus 3h, which is exactly equal to 200 minus 6x. So let's write that again. So we found that the marginal revenue is equal to the derivative of r, which we computed to be equal to 200 minus 6x. So now the question is, what is the marginal revenue when 30 units are sold? That means that we want to know what is the marginal revenue when 30 units are sold. So for this part, we need to only evaluate the function. So we will get that this is 200 minus 6 times 30, which is 200 minus 180, which is equal to 20. So the derivative now allows us to compute marginal revenues given a revenue function that is not linear. Now we can compute the marginal revenue when the revenue function is a polynomial. To summarize this video, notice that all the following concepts relate to the derivative of a function. So the first motivation was to find the instantaneous rate of change of a function. We also found that the derivative is equal to the slope of the tangent to the graph of the function. And some particular instantaneous rate of change might be the velocity of an object, and also the marginal revenue for a revenue function. We can do the same thing, in fact, for the marginal cost for a cost function, and we will see several applications of the derivative throughout this course.